Hello, my name is Lev Zelik, and welcome to Pump Video Academy Online, module PVA number 7. My assistant, my trusted assistant, Ms. Maya Khan, is recording the session, and during the session we'll do an experiment of testing the actual pump efficiency. And we're going to compare this efficiency to a predicted or expected value. If you work at a power plant or a chemical plant or water plant, you have pumps. How efficient are those pumps? Are they 80% efficient, 70, 10? If they're 80% efficiency, should they be 90 or perhaps 60 or 65? That's all they're capable of delivering? Well, those discrepancies between expected efficiency and actual efficiency are subject to other modules of our program. Today, we'll focus on actually measuring efficiency of the existing pump. And the results might surprise. So first, let's talk about pump efficiency definition. Pump efficiency is defined as a ratio of the fluid power divided by the total power delivered to the pump. Let's call it good power in quotes divided by total power. Total power is kilowatts or horsepower delivered to the pump. In our case, we cannot, as often the case in the field, it's impossible to measure the power to the pump. You can only measure the pump delivered to the motor. So we're really measuring a combined effect on the system, pump and the motor together. The good power, the fluid power, is equal to flow times pump head, as we described in other modules of pump performance, multiplied by specific gravity, and divided by 3960 in the US units. Gallons per minute, feet of head, specific gravity 1.0 in our case, where we have a tank with a clean water supplying fluid to the suction of the pump, and then through a flow meter and a set of valves recirculating it back to the tank. The last modules, several modules, we discussed how the pump head is calculated, that being the difference between a discharge minus suction times 2.31. Discharge minus suction times 2.31 in the US unit will produce the pump head. So let's do an experiment. We will see how the efficiency flushes out through a formula and the measurement. So let's start the pump. Well, you immediately see that the discharge gauge is showing 2.5 psi gauge. The suction gauge is approximately 2 inches of mercury, minus 2 inches of mercury, slight vacuum, and 2 inches of mercury is roughly 1 minus 1 psi. The difference between 2.5 and minus 1 is 3.5 psi. And that's the differential pressure. Times 2.31. Get it? 8.1 feet. 8.1 feet of head. The flow is 3.2 gallons a minute, as I'm reading it off the flow meter. So that the product of 3.2 times 8.1 divided by 3960 and times specific gravity 1.0 according to the formula ends up being 0.2065 horsepower. And if you multiply it by 746, we also did that in earlier pump school sessions and in the Pump Video Academy. We went from the horsepower to kilowatts, or 2 watts in this case. So times 746 is 4.9 watts. $4.9. The total power is measured by the power meter that is connected between the power supply and the motor to the pump. It is registering 108 watts. 108 watts. So we're going to write it down. So that the ratio of the good power, 4.9, divided by total power, 108, times 100, in order to get percentages of efficiency, will be guess what? 4.5%. Many of you might be surprised. A centrifugal pump, 4.5% doesn't sound like a lot. Why is that? We would like to hear from you. Any ideas on thought? What made this pump, this particular experiment, so inefficient, perhaps? Or perhaps that's the best we can expect in this kind of a pump. We'd like to hear from you. Send us your emails, call at drpalm@pumpingmachinery.com, or visit the website at www.pump-magazine.com. You can see the pump school schedule, in which we'll cover this topic in much greater detail. And until then, I'd like to extend again my thanks to my assistant, Ms. Maya Khan, and keep on pumping.